Okay, so we're going to have a quiz on eigenspaces. And so the question will be, given a matrix, find all eigenvalues, of course, and therefore also find the basis for each eigenspace. But of course, if you have to do this, you have to even first find the eigenvalues first. So I'm giving a 4x4 just to show you that how to do this. It's a bit more variation, but this is quite lengthy. So even a 3x3, you'll see it's going to take you, if you do, it's going to take a little bit of time. Okay, so prepare yourself for this quiz. It's going to be a bit longer than most quizzes because it's a bit more work that you're going to have to do. Okay, so better know also what you have to do. All right, so here we go. Step 1 is, of course, finding our eigenvalues. That is the characteristic equation. And we do this by, in the matrix, replacing the diagonal, subtracting lambda at the diagonal. So it's determinant, so this way. So we have minus lambda. So on the diagonal, I subtract lambda, and all the rest I copy. So subtract lambda, copy, 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 subtract lambda, copy. 2, 1, 0, and subtract lambda. Now, especially when you have determinants of bigger size, you want to find a good way to quickly get this determinant. And first thing you should always look for is there any row or column where I have a lot of zeros, meaning all but one. And this is the case here, namely row 3. And so that means that I take this factor out, which comes with a positive sign, and therefore after I take that factor, the cofactor is left is minus lambda 2, 0, 1 minus lambda 1, 2, 1, 2 minus lambda. Okay. When you're 3x3 and when you have not such a row or column that I was just pointing out, you could still do expansion along one of the columns or rows. The best one would be column 3 here, but you would have to work it out. And perhaps it's not that longer here, but I'm going to do still the row operation. So what I'm going to do is I'm going to use this pivot here to get a 0 here. That means I have to multiply this with lambda minus 2, right? So what I'm going to do is row 3 plus lambda minus 2 times row 2. Right? Now, lambda minus 2 is the negative, of course, of 2 minus lambda. Okay, so let's work that out. Now don't forget we have this minus lambda in front. We have to keep dragging that along. Minus lambda 2, 0, nothing happens here. 1 minus lambda 1. And so now I multiply this row with lambda minus 2 and add it up. So I get lambda minus 2 plus 2, that's actually just lambda. Then I get 1 minus lambda times lambda minus 2. I cannot really work it out, so I have to expand this at some point. And then the last one, of course, should just give 0, right? That's the whole point. Okay, so now I can do again column 3. So here this was row 3, right? And so we have the lambda, this lambda. Then this 1, which of course we don't write. It comes with a negative sign, actually, plus, minus. So, okay, let's get rid of that line. And so what I'm left with is minus lambda 2 lambda, and let's work this out. It is 1 minus lambda squared minus 2 lambda. So minus lambda squared minus 2 lambda, no, plus 2 lambda, plus 2 lambda, plus 1. And this 2 by 2, I just use the formula. That's lambda. And then we have the product of the diagonals, minus lambda times minus lambda squared plus 2 lambda plus 1, minus the product of the other two off-diagonal elements, that's 2 lambda. And so this one I expand, that is lambda cube minus 2 lambda squared minus lambda minus 2 lambda. So I get lambda cube minus 2 lambda squared minus 3 lambda. Now I'm still stuck with the third degree, and that is even those are very hard to, in general, to solve. We discussed some options like testing for possible roots. Now your first thing, I will never give you very complicated things. So if you get an equation that you cannot solve, you did something wrong. And so what you need to do here, what you're often going to have is a simple factorization. And here you see you can factor out another lambda. So we get actually lambda square, and I have lambda square minus 2 lambda minus 3. And so now we need two elements that multiply to -3 and add up to -2, and -3 plus 1 will do the job. Okay, so now this is the determinant, and so we have to put this equal to 0, and this gives me lambda is 0, lambda is 3, and lambda is -1. Notice that here we have lambda is 0 is somehow twice here, okay? Because we know that the 4x4 should have 4 eigenvalues, but sometimes some are counted twice. In this case, lambda is 0. That's step 1. That's relatively easy, if at least if I give you a nice determinant. The other one is not hard either, they are lengthy. So step 2, now we have to find the eigenspace, or the basis for the eigenspace for each of these eigenvalues. So let's start with lambda equals 0. And what would we need to do then? We take this matrix A and subtract lambda from the diagonal. Or, same thing, put in lambda equals 0 into this expression. Okay, but with of course the in this expression, right? Okay, so, but of course, subtracting lambda is 0 from the diagonal means you don't do anything, so it's actually the original matrix. Okay, so the original matrix is, I have it written down somewhere so I don't have to scroll up all the time. It's 0, 0, 2, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0. Look, that's already nice, we have a 0 there. 1, 0, 2. Okay, first of all, I need my pivot to be on top. So I'm going to exchange row 1 and row 2. Okay, I'm going to rotate that. If you try to be fast here, the problem is you get lost in the numbers and you keep copying things wrong. So it is better sometimes to not go too fast. Now, in this particular case, I want to swap these 2 rows, but I do want to get the 0 rows in the back, so I'm going to also swap these 2 rows. Okay, so that would be a 2, 1, 0, 2, and a 0, 0, 0, 0. So I have already a 0 in the bottom, which already tells me that will have an a basis, right? There will be a free vector, a free variable. Okay, but we keep going. We need this is a pivot, so we need a 0 there. So the row operation that I'm going to do is row 3, replace that by row 3, and subtract from that twice row 1. Okay, so what we get? 1, 0, 0, 1, 0, 2, 1, 0. So multiply this with -2 and then up here. So -2, 0, 0, -2. No. What am I saying here? Sorry. I'm adding it. Sorry about that. Okay, so -2, I'm adding this to that. So that's a 0, then I have a 1 here, 0 plus 0, and then a -2 plus 2, that is a 0. Okay, so, and then we have 0, 0, 0, 0. Again, I want my pivot 1 here, so the easiest way is to just swap them. Row 2 with row 3, and I get 1, 0, 0, 1, 0, 1, 0, 0, 0, 2, 1, 0, and then this is 0, which I'm not going to write anymore. So I have my pivot for which I can now make a 0 there. So row 3 minus 2 times row 2, and I get 1, 0, 0, 1. Sorry, I'm going this way and then this way and this way. Okay, so now I'm going this way. 1, 0, 0. 0, 1, 0, 0, multiply this with -2 and add up this one, so it's 0, 0, 1, 0. Okay, great. And actually, this is very good because although normally at this stage I'm only in echelon form, I'm actually already in reduced echelon form. And I can analyze the whole thing. I have the 3 pivot variables, x1, x2, and x3, and I have 1 free variable, that is x4. So I write everything in terms of this free variable. This one tells me that x1 is equal to negative x4, x2 is just 0, x3 is also just 0, and x4, of course, is always equal to itself. Again, if this is not clear, what does this mean here? This means 0 times x1 plus 1 times x2 plus 0 times x3 plus 0 times x4 is equal to 0. So x2 is equal to 0, etc. Okay? And whatever we find here, we factor out the variables, the free variables, as many as there are. In this case, there's only 1. So this means that dimension, when we talked about dimension, is 1 here. Okay, so we have a single basis factor here. This is a basis factor for the case lambda equals 0. Okay, so lambda equals, what were the other two? 5 and, no, no more using. Lambda equals 3. So we take our matrix. I'll copy the matrix again. It was 0, 2, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, and 2, 1, 0, 2. And this time I subtract 3 from the thing. So this will go minus 3, minus 3, oops, minus 3, minus 3, and minus 1. Okay? And I have a pivot here, this 1 here. So I'm going to use that first to get it up. So the operation do is row 2, replace that with row 1. I get 1, negative 3, 0, 1. I have to make sure that I don't miss my negative signs there. 0, 0, negative 3, 0. Oh, but I can already see that I should also perhaps, in this row here, I can already divide by negative 3. Let me do that at the same time. So row 3 divided by minus 1/3 of row 3. So that this one is actually already 1 here. And then in the bottom 2, 1, 0, negative 1. Okay. I use this pivot to make the zeros below. That's row 2. No, let me write it here. Row 2 replace row 2 plus 3 times row 1, and row 3 replace row 4. Sorry, replace row 4 minus 2 times row 1. Okay. So we get 1, negative 3, 0, 1. So we multiply this with negative 3 now first, and add, with positive 3 and add up. So 0, negative 9 plus 2 is negative 7, 1, we're multiplying with 3, 3. Okay? And then 0, 0, 1, 0. And now I multiply this with negative 2 and add up there. That is 0. 6 plus 1, that is 7. 0 plus 0 is 0. And minus 2 minus 1 is minus 3. Good. This is, I see what happens, right? I notice that row 2 and row 4 are almost the same, so they're going to cancel each other out. Unfortunately, I don't have a pivot, so I'm going to have to make a pivot by dividing, and this, I said, I'm going to warn you. I'll try to give you problems where as little as possible fractions will appear, but it's almost inevitable in certain questions to have fractions. So don't panic if you see once in a while a fraction. It should never be huge things, nothing out of the ordinary. Okay, so here the fraction that I'm going to get is a 7, so I'm going to divide by minus 1/7. Okay, so I get 1, negative 3, 0, 1, 0, 1, minus 1/7, minus 3/7. 0, 0, 1, 0, and then 0, 7, 0, 3. Now, for sake of a little bit quicker, I'm actually noticing that, sorry, I'll do this in red. I'm actually noticing that if I would add this row to that, I get 0. You shouldn't do this, but sometimes it's so obvious that you want to get going, okay? So I do row 4 replace row 4 plus row 2. Okay, so I get already a 0. So this would be a 0 then. I have to add I'm just adding the rows, right? So 0 and then here a 0. That's 1 and then a 0. Okay. And now I see again that these two rows are going to cancel out, the two bottom rows. So I'm going to do here row 4 minus row 3. So let me write down what I have now. 1, negative 3, 0, 1, 0, 1, minus 1/7, minus 3/7, 0, 0, 1, 0, and then 0 rows here, 0, 0, 0, 0. Okay, so we have our pivots, but we need zeros on top of it. So the couple of things I have to do, one at a time. So row 2, plus 1/7 of row 3. Okay, I'm now working my way backwards, right? I'm using this to get there. Okay, so that will give me 1, negative 3, 0, 1. So what I'm doing, I'm multiplying with 1/7 and add, so I get 0, 1, 0, minus 3/7, 0, 0, 1, 0. Great. And now the next thing I have to do is the row operation. I have to get rid of this guy. So row 1, replace that with row 1 plus 3 times row 2. And I get 1. So am I multiplying this guy with 3? That's what I said, right? Yes. So 1, that gets a 0. That's still a 0. And then minus, so I get 1 minus 9/7. That is 7/7 minus 9/7 minus 2/7. Okay. And this is just copying 0, 0, minus 3/7, 0, 0, 1, 0. So we have our pivot variables, x1, x2, and x3. And we have our free variable, x4. This means that I can write x1, x2, x3, x4. x1, this is from here I see what x1 is, namely it is 2/7 of x4. This tells me that x2 is 3/7 of x4. This tells me that x3 is just 0, and of course x4 is just x4. So we get x4 2/7, 3/7, 0, 1. Okay, so that's definitely a good, that's a basis factor, and that's all what I asked. Now, I want to show you that you can check your answers, because if everything what you've done is correct, then this should be the eigen, each of these vectors should be an eigenvector. Now, you don't want to work with fractions, so even here you would say, I'm not going to check this with fractions, but you have an option, because this x4 here can be any number here. Any number you take will give you an eigenvector, and any one will be a basis. So I can take here x4 equal to 7. So this is, I'm putting this here between parentheses, checking your answer. I don't expect you to do that, but it is something, if you have the time, and it's a good practice, you can do this. Namely, you can say, okay, I'm going to take x4 equal to 7 here. In the first case, there was no need to take something weird. I just could take x4 equal to 1. And then you can double check that minus 1, 0, 0, 1 would have been an eigenvector. But okay, coming back here to, I don't want to do all cases, but I want to show this case. So why do I do this? Because then the vector becomes 2, 3, 0, 1. Okay? So I can now ask, if I take this vector, what is it, 2, 3, 0, 1, remember, I'm going to multiply it with the original matrix. Okay, give myself a bit of space here. And so I get 2, 3, 0, no, 2, 3, 0, 7, right? What did I say? Hey, Bob. x4, I'm putting x4 equal to 7, so this should have given me 7 there. Everything multiplied with 7. Oh, okay. 2, 3, 0, 7. Yeah, of course, it's not very helpful if you want to try to check something and then you use the wrong thing. Okay, good. So let's work this out. Remember, you go through this row while you go to this column, multiply and add up. 0 times 2, that's 0. 2 times 3, that's 6, plus 0, plus 0. So I get 6 for the first element. Keep doing that, do the same for the second row. 2 plus 0 plus 0 plus 7, I get 9. 0, 0, 0, that's going to be 0. And then I have 4 plus 7, 4 plus 3, that's 7, plus 14, that's 21. Now, this should be what? You see it already, but what should it be? if everything is correct, lambda is 3 is the eigenvector, so this should have been 3 times my previous vector. 2, 3, 0, 7, and that's exactly what it is. So that's how you verify that you have done the right way. Okay, but I told you it's long because there is still one more eigenvector value left, that is lambda is -1. So lambda is -1. Again, I take my original 0, 2, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, and 2, 1, 0, 2. I'm writing it small because I know I'm going to subtract. Subtracting 1 means actually adding 1. So this will be a 1, this will be a 1, this will be a 1, and here adding 1, this will be a 3. Okay. Good news is that I have already my pivot where I want it to be. So I'm going to use this pivot, and therefore the row operations that I have in mind are row 2 minus row 1, and row 4 minus 2 times row 1. Okay. So the first one is 1, 2, 1, 0. Minus, I'm subtracting, so 0 minus 1, minus 1, 1. Okay. And the other one is I multiply with -2. I better write it because if I don't write these numbers down, I get lost. Minus 2. Oh, so no, of course this one I just have to copy. Now minus 2 and add up, that is 0. Minus 4 plus 1 is minus 3. Minus 2 plus 0 is minus 2, and that is just 3. Good. I need a pivot here, which I almost have. So the row operation I'm going to do, but I'll do this in purple, meaning I'm going to afterwards erase it. I've changed the signs, okay? And I'm going to do this just boop, boop, and boop. So now I don't need to do this anymore. So the row operations that I want to do now, I get 1 and 0 here, so I do row 4 plus 3 times row 2. Good. So I have 1, 2, 1, 0, 0, 1, 1, -1, 0, 0, 1, 0, and then multiply this with 3, add up 0, that's a 0, 3 minus 2, that's 1, minus 3 plus 3, that's 0. And now it's clear that the last one here, row 4, row 4 minus row 3, using this pivot, I'm going to get my echelon form. 1, 2, 1, 0, 0, 1, 1, minus 1, 0, 0, 1, 0. It's not continually done. This is echelon form, so I know already that I have 3 pivot variables and 1 free variable. I know I have to have at least 1. In fact, there's more that you know. And if you listen to today's lecture, because lambda, look at what happens here. Lambda is 0 is a double root, and therefore it means that there can be maximal a basis of length 2. In other words, the dimension of the eigenspace can be maximal 2. Although we have found actually there's only a single basis, so dimension is 1. But here, this lambda is 3 is only a single root, so the dimension can be at most 1, and the same here. So, in other words, remember the dimension is the same as the number of free variables. Okay, so, but going back to the calculation, I use this one here to get row 2 minus row 3, and also there, row 1 minus row 3. This gives me 1, 2, 0, 0, 0, 1, 0, -1, 0, 0, 1, 0. And then the final thing is this one here, row 1 minus 2 times row 2. I'm left with, so I'm multiplying this with -2, right? So, yeah, by the way, I didn't write the bottom 0 row anymore, right? So there was a 0 row here, sorry, but I stopped writing it. 1, so -2 up there, no, that's just a 0. -2 times -1 is 2, added up, it's a 2. 0, 1, 0, -1, 0, 0, 1, 0. Okay, my free variables are x1, x2, and x3. And I have my pivot variables, what did I say? x4 is a free variable. Okay. So x1, x2, x3, x4. These are, each of these blue exactly the equation that I need to solve for x1, x2, and x3. So for x1, I see that I get minus 2 times x4. Remember, it always has to be, this is always equal to 0, right? This is what this means, so you have to bring it to the other side. Then, so the other one, therefore, is plus x4. This one just tells me that this x3 is 0, and here x4 is x4. So bringing that out, I see x4, I get minus 2, 1, 0, 2, 1. And so you can again check that this is an eigenvector. Okay, let me just quickly do it. Minus 2, 1, 0, 1, right? Okay, so I'm going to erase this here. Just double checking that everything is good. Minus, right, okay, now I lost myself. What was it? Minus 2, 1, 0, 1. Minus 2, 1, 0, 1. What I get? Minus 2 is 0, 2, I get 2. Now, minus 2 plus 0 plus 0 plus 1, that is minus 1. That is always 0, because the whole row is 0. And then for the last one, for this element, I do minus 2 times 2, that's minus 4. Plus 1, plus 0, plus 2. That's minus 1, okay? Now, we know that the eigenvalue was negative 1, so this should be negative 1, the original guy, and that's exactly what it is. Okay, so again, check that we are done. Okay, so I told you, it's quite a long quiz. Of course, I took my time explaining things, and I guarantee you, I will not give you a 4x4, a 3x3, and I'll make it so that you don't run into back problems, but you're going to have once in a while fractions. So that doesn't mean that you make a mistake. One thing I want to point out to connect it to today's lecture is that going back to these dimensions of these eigenspaces, we saw that each of them has dimension 1, right? But that's bad news as far as diagonalization goes, because that means we only have 3, but where we need a 4x4 for P. So the P here that we normally would form cannot be formed because there are only 3. And therefore this means that A is non-diagonal, not diagonalizable. So here you see an example of a matrix that is not diagonalizable. And to prove that it's not diagonalizable, it's not that I could make a shortcut here. This is what I needed to do. I know, terrible, right? Well, terrible, it's fun. But very, very careful with negative signs, pluses, no zeros. Write down every single row operation, take your time. Okay, you have the whole class time, and in fact, if you're a bit late, it's fine with me. Okay, so make sure, I mean, a bit late doesn't mean 5 days later, right? It means by the end of the day. Okay, all right.